Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest. This is an interesting problem and this is little trickier than the usual problems. But in this video, I've tried explaining two different approaches, one of the same problem, and those two approaches are completely separate from each other. You will look at it, but uh, after watching this video, you should be able to understand how to come up with recursion states or DP states for that matter to solve any problem or how to think about the states in the first place. Okay, so I would encourage you to watch the video till the end. It might be a little long, but let's see. I will try to finish everything in as much less time as possible. So with that, let's start. You are given robots and factories. You can read the problem statement yourself. The problem statement is a little bit complex, so I'm not going through the entire problem statement. But after reading the problem statement, you will understand how complex the problem statement is and how simple the solution that we are discussing is. So you are given some robots. ith position denotes the position of the ith robot. Similarly, you are given some factories. ith factory denotes the position of ith factory and how many robots it can repair. Okay, so each of these robots needs repairing. So they will be getting repaired in one of these factories. So the positions of each robots are unique and position of each factory is also unique. Now they are saying that robots can move either left or right, and at any moment we can change the direction of the movement of the robot. Okay, so now the question is to get this robot repaired at some factory, this robot needs to travel some distance, right? So you have to determine the minimum distance traveled by all the robots to get repaired. So for example, there are three robots and there are two factories. This robot, we have set this direction to the right and set this direction to the left. So this robot will be repaired at this factory. This robot will be repaired at this factory. And the limit of this factory is 2. So this is okay. It can repair both of these robots. Now, if you look at it, this was at position 4, factory was at position 2. So 2 unit of distance it has to travel. Similarly, it was at position 0, the factory was at position 2. So again, 2 unit of distance it has to travel. So total 4 unit of distance these robots have traveled. Now for this one, it doesn't travel any distance at all because it was repaired by this factory. So that is the optimal approach. You can't. So in this approach, you have like the robots have to travel 4 unit of distance. So that is the minimum possible that you can get. You can try any other combination. You will not get any assignment such that the distance traveled is less than 4. So that's the answer. Now there are a lot of things in the question. Robots are moving. We can set the direction. Robot needs to be assigned to a factory. Factory has some limits. So whenever this kind of problem comes, the first thing you should be doing is try to simplify the problem. Try to take a case where there is two factories or one factory, two robots or three robots, and then try analyzing the problem. Once you have done that, you have like what exactly we are doing. We are trying to simplify the problem and try to see what happens if there are two or three factories, or what happens if there are two robots, and trying to determine some observation from there. And once that is done, the problem will itself be simplified. Okay, so let's look at it. Let's say this is the robot arrangement. There are two robots and three factories. Okay, now you decided to assign this robot, like you have to assign these robots, right? So let's say you can assign this robot to this, or you can assign this robot to this factory, or you can assign it to this factory. Now which one you will assign? This factory was at 3 unit of distance, this factory was at 3 unit of distance, and this factory is, let's say, x, like very long distance greater than 3. Now you notice that this factory and this factory was at same distance. So which one you will choose? The answer will depend on the next robot. Let's say the next robot, for this robot, this was at unit distance 3. This is at distance of unit 2. So you will try to assign this robot to something which is at less distance, right? So you will be assigning this robot, or you will at least try to assign this robot to this factory. And then, because let's say the factory limit is 1, let's just simplify it. The factory limit is 1. So if you have assigned this already, you can't do this assignment and you have to assign this. So notice what happened. The assignment of a robot actually depends on the assignment of other robots as well. So with this, what we have observed is we have to apply, or we have to assign all the robots to get a minimum possible distance covered, right? So basically, you have to try all possible combination of assignments to get the minimum possible distance. That is clear. Now, whenever all possible assignments are there, either you will do brute force or you will try to come up with some recursion so that you can transform it to, like, you can memorize it to a DP solution. So in this problem, as because this is an assignment problem, assignment, if you try to come up with brute force, it would be something, choose something, like this is combinatorics. And you can, I am not deriving what these values are, because otherwise the video will again be long. So I would, if you want this, I can we can discuss this in the comment section below. But this solution would not work, right? You can't actually enumerate uh, all possible assignments. So now you have to come up with some uh, recursion states. Now before that, let's make some more observations. Let's try to see if we can make some more observation. Let's say you assign this robot to this, or maybe let's say you assign this robot to this. So can you ever assign any robot after this to this? Think about it. The answer is no. Because if you have assigned, like let's say this was at position x, and this was at a position some x plus y. Okay. Now this is at position p, and this is at position p plus q, right? So what you have just done, you have assigned this robot so that you get p plus q minus x, right? This much distance. And similarly, you have assigned this robot to this. So what you get x plus y minus p, right? So instead, what you could have, like, if you have done this, a better would, like, it is always better that you make this assignment instead. W- And you can see, if you make this assignment instead, you will be getting x minus p plus x plus y minus p plus q, minus p minus q, right? And this, if you find out, this is actually smaller than this. So basically, it is always better to assign, it is always better to assign assign robots to a factory which is actually in the sorted order. So basically, if you have assigned something to this factory, you will never be assigning a robot to a factory before this last factory assigned. Okay. So what we have just said, like discovered, is assignment actually uh, will be done in the sorted order. So basically, this factory will be getting some of the robots, right? And then this factory will be getting some of the robots, and then this factory will be getting some of the robots, right? So this is the way you will be assigning, right? Now, if this point is clear, let's now come up with our recursion states. First, we have to find out what is our recursion state. So now, to find out what is recursion state, one thing that you should be always keeping in mind is, you if you are at some recursion state, which, let's say, consider this robot, it should not matter, it should not ever matter that you will care about what happened with this robot. If you have moved to a particular robot I, it should not matter what happened with any of the robot before I have tried explaining this concept in much more detail in this video. I will strongly encourage to watch this video once. So I have tried comparing two similar problems, very similar problems, and how DP state works there. So I would encourage you to watch this video. But the gist is, if you have assigned some robot, or if you are assigning some robot I, it should not matter what you have done to any of the robots before I. Okay. So with that, now what we have just discovered like was that you will be assigning some robots to this factory, and then some robots to this factory, and then some robots to this factory. This is the way you will be assigning, right? You will never be doing this, or maybe you will never be doing this thing like this, some factory, let's say F here. You will never be doing this because of the reason we discussed. Now, uh, if you are doing this, so what exactly your DP state can be? Basically, you are solving the same problem. Let's say you assigned some robots to this factory. So in a way, what you can say that, okay, my problem is now reduced. I can assume that this all thing doesn't exist at all, and this is the first robot, and this is the first factory, right? So that is what we are doing. Like we are saying that we will assign some robots to this factory, and once we have done that, it doesn't matter at all what we have done with the previous approach, previous robots and factories. I will be starting with this new factory, and I will be starting with this robot first. So this is the reduced problem. So we are solving the same problem. Like we are given some robots and some factory, we have to do the assignment. Exact same problem, but with reduced constant. So hope you can see the recursion. So what we will do, or what is the recursion state? Recursion state would be, what is the first factory that I am considering, right? And what is the first robot which is unassigned? That's the recursion state. Now, what will happen in this recursion? As mentioned, this factory will be taking up some of the robots after this robot, right? So this factory will be taking up some of the robots after this. Or it may happen that it will not take anything. That may also happen. So there are two state, or rather, let's say the limit is L. Now okay, let's solve with one limit one only first. Let's say limit is L. So if limit is L, you can actually take 0 robots, you can take 1 robot, you can take 2 robot, all the way up to you can take L number of robots, right? So these all will be your state. So what exactly you will be trying? You will be trying out each of these possible combination. So what does we mean by taking 0 robots? We will say that, okay, this factory doesn't have, we will not assign anything to this factory. So we will go ahead with the next factory. So next factory is Fi plus 1, and we'll start with this robot itself. Okay, so in a way, what happened is, we have removed this factory from our question altogether, and we are saying that this is the new problem. Okay, now what exactly we mean when we say we have to remove 1 robot? What we are saying is we will move forward with the next factory, right? And next factory would start with robot assignment from this index. What exactly this mean? This means that we have assigned this robot to this factory. Now the new problem is this. Okay, so hope you get the intuition. So this is one possible state. And remember, as discussed, while considering any, while we are at factory I and robot I, we don't care what happened to any of the factories before this or any of the robots before this. That is completely useless at this point. Okay, so this is one possible approach. Let's look at the pseudocode. Pseudocode is very similar to what we just discussed. Uh, we have two things, index and robot. We will try repairing our robots in this factory. And how many robots we can repair, it depends on the limit of this factory. So that's we will this our robots will be in this range, right? And for each of these cases, we will try to find, let's say if we repair our robots, let's say if we repair 1 robot, so this will be the new problem, right? But for this robot, we are saying that I will be assigning this to this factory. So you will just add the cost of position of robot I and position of factory I, right? So because this is the cost of repairing this robot, right? Hope this makes sense. So what we are doing, we are just finding out, trying out every possible combination and finding out the cost of repair, and then calling the next factory with the next robot. Okay, so hope this makes sense. Let's look at the code for this first, and then we will come back and discuss another possible approach. So the code is again very similar to what we just discussed. We will sort the robots and sort the factories, because as discussed, we will be assigning, like we will not be doing things like we will assign this robot to this and this robot to this. That is not optimal. We have already discussed that. So because of this, we will sort these two things and assigning them in the order. Now, these two are just global variables for to make this recursion state clean, and this is the DP array. Like we have to memorize it, right, to just ensure that we are not calculating the same state again. Now, if we have exploited all the robots, it means all the robots are assigned. So we require zero distance to be traveled more. That's why zero. Now, if we have exploited all the factories, it means all the factories are exploited, but not all the robots are assigned. So this is not a valid combination at all. So we will return something very greater, which is infinity. Now, if not, we will try to see if we have actually calculated the state previously as well. If we have, we will return that. Otherwise, we will start. Now, what exactly we will do? We will try to repair some robots. Like this is the capacity of the current factory, and this is the position of the current factory. Okay. Now we will try to repair robots. We can repair zero all the way up to the capacity of the factory. Now repair cost is zero, like we'll try to find the repair cost. We will come to that, but let's say we find the repair cost. Now once we have repair cost, we will know that okay, this is the repair cost, and we will now try to assign something to the next factory starting from this particular robot. Okay, and how this robot is coming into picture? This robot is just number of robots we have repaired. Okay, so and now repair cost, everything, every robot that we are repairing with this factory is coming to this particular position, right? So we will just add the difference between the position of the robot and the position of the current factory. Okay, so hope this solution makes sense. Now let's try to think of, like we have think of it in terms of factories. So basically we are saying that at every iteration we will be removing at least one factory, right? Now let's think of in terms of robots. At every iteration we will try to think like in terms of robots. So let's remove all of this and let's try to think about it. Okay, so the observation that we have made will still remain. Okay, so uh, we we have made that we will not assign this robot to this factory and this robot to this factory. This can never happen. This observation will still be there. Now let's think about it in this way. Let's say we have to only care about robot. We will not care about how many robots or how many factories can be assigned, like how many robots can be assigned to this factory. We will just care about the current robot in hand. That's all. So what exactly this robot can do? It can be assigned to this factory. Okay, or it it will say that okay, I will not be assigned to this factory, let me try with some other factory. Okay, so in a way what you're saying is you have f of I, which is the factory index, r of I, the robot index. You are saying that either r of I will be assigned to this f of I, or it will not be. That's the two possible that's the two possible case, right? Right, that is also true. Now think about it. We have said that, like now let's say what are the state. Let's try to enumerate the state first. We will get to know the issues here. So we are saying either it will be assigned to this index or it will not be. So if it will be assigned, what will be the next state? Next state would be that this robot, let's say there are some robots after this as well. Okay, so all this robot can also be assigned here, right? So what you will say, you will not increment your factory index, rather you will just increment your uh, robot index and just add the contribution of the distance, like distance between this and this, right? This is good. But now let's say the next robot is this. So can this robot be independently assigned to this factory? Answer is no. So if you remember, in the starting of the video we discussed that the case of recursion is such that, should be such that, if you are at some robot I, you should not care about what happened with the previous robots. Or if you are at factory I, you should not care about what happened to the previous factories. But here, that is not the case. If you have assigned this robot to this factory, you have to know what is the limit of the factory left, right? Otherwise, you will also assign, let's say the factory limit was 1. And if you have assigned something to this factory and you move forward this factory for the next robot can also be assigned to this factory, but that is not a valid assignment because this factory can only hold or can only repair one robot, right? So hope you see the like difference here. Basically, we are not able to independently say that okay, I will be as like if this robot is assigned to this factory and if I move forward, then this robot can independently determine whether it will be assigned to this factory or not. This is not happening. But we need this. Again, I will encourage you to watch this video first. You will be able to understand what we are trying to talk about here. So the crux is, at this state, we are not able to independently determine whether I can be assigned to this factory or not. So for that, we will just add another thing. Instead of like apart from these two things, we will also add limit, right? Limit left. So we will try to add what is the limit left. So initially, this first factory has some limit L, right? Now, once you assign some robot to this factory, again the same thing. Either you will assign this robot to this factory or you will not assign. So if you assign this robot to this factory, you will say that okay, factory is same. I have assigned this robot to this factory, so I will increment the R, and limit is also decreased. Okay. And similarly, if you haven't assigned anything to this factory, you will say that okay, I will not assign anything to this factory. So just increment the factory and keep the keep this index because I am yet to be assigned, and the limit would be the limit of this new factory. Okay, so now the state is clear. Now if you are at, let's say, this robot I, you know, if you have to be assigned to this factory, what is the limit left and whether this can be assigned to this factory or not. So this is now independent of what happened to all the R's before or all the robots before, right? So hope you see the difference. So basically, we are trying to just see, like for every robot, we are trying to say whether it will be assigned to this factory or it will not be assigned to this factory. That's the two possible combination. And to make things independent of previous robots, because that is required. Otherwise, you will not be the assignment would not be correct. To make things independent, you have also taken a third parameter, which says how many robots are left. So how many limits are left for this particular factory. Okay, so what will be the pseudocode? Pseudocode will be exactly similar. uh, we just have a limits left in our state now, and if limit left is 0, it means we can't assign this robot to this index, so this state can't be reached. So we will just return this new state, like, because this state can't be reached, right? Otherwise, there are either you can do this or you can do this, right? So what we have done, we have say that okay, I will not assign anything to this index, to this f of index. I will assign it to the, I will just move forward, or I will be assigned to this index. So I will not, I will move forward, but limit left would be -1, will be decremented, and this is the assignment cost. Okay. And again, you can just memorize it and it will work. So what is the time complexity of this solution? The time complexity is like inside this we are not doing anything, any for loop or anything like that. So time complexity will simply be number of possible states. So what are the, like let's say there are f factories, each factory has some L limit, and let's say there are R robots. So time complexity would be F into R into L, right? So this is the time complexity of this approach. And what was the time, like I am not implementing this because implementation would be straightforward. So you can implement it yourself. And what is the time complexity of the previous approach? So if you look at previous approach, we have these two things like F index and R index was there. So F and R are there. But inside each state, we are doing two for loops. First for loop is based on capacity, and second for loop is again based on capacity, like how many we have taken. So this is L square, right? In worst case. So this was the complexity previously, and this is the complexity now. Now I claim that you can also optimize this loop by doing some kind of pre-computation. So I will give it you to an exercise that try to do some kind of pre-calculation to optimize this inner loop. You don't need it. We don't need this inner loop at all. So if you don't need inner loop, this L square will also be L. So the final complexity is F into R into L. Okay. So hope you enjoy the solution and learn something new. Every time, again remember to come up with some DPs or to solve any kind of hard problem. The first step should be to optimize the problem and try to make some observation. Once you have made the observation, you will be able to either solve the problem or actually comment on the complexity of the problem. And then once you have identified if it is like if it is already solved, that's good. And if it is DP, you have to make sure that the recursion states that you are coming up with should be independent. That is, if you are at ith index in the recursion, you should not care about what happened with the previous index at all. Okay, so that's it for this video. If you like it, give it a thumbs up and do subscribe if you haven't already. Again, watch this video to get much better understanding of the same concept that we just discussed. And as an exercise, you can just implement the next solution. You can try to optimize this. And a bonus would be you can try thinking about what exactly happened when this constraint was not there, or for that matter this constraint was not there. Think about it. It is very very interesting. You will get much more. If you want, we can discuss this in the comment section below. Okay, thank you.